All right. So what do we got?
Ethan went for the rough classroom. He's in log 207 right now.
Oh. Yeah, he thought I changed the review session to that, right? Oh, oops.
Well, I think also, didn't we have the review session last time, there?
Oh, yeah, probably. There was some reason. I don't think he's gonna last long in there because I think there might be an exam in there. So I think that's what I got this one.
He's gonna get sent away. But the next exam slot is until 7 p.m.
Oh. Oh, yeah. So are we in part of the period now?
Yeah,
Yeah.
the exam period.
So I guess there's not anybody in there. I guess, or it wasn't. Yeah, maybe there's an exam at 7 or something. I forget. There was a reason. So what that was.
I'm looking at the final exam gate back in spring 2013. There are a few questions on just like some of your definition questions.
I actually have several ones.
For H, it's really vague. So what were you looking for?
Sure. You should make sure that we're clearly recording on my comments here. So, which one? H?
H, yeah. What were you looking for there?
Okay, so, well, let's see what we can come up with. Suppose phi F A is a homomorphism. What are some of the adjectives that we apply to homomorphism, right? Isomorphism, metamorphism, monomorphism, etc. What isomorphism or what adjective always is true for a homomorphism fields? They're always they're always 1 to 1. That's right, exactly. Because the kernel has to the only ideal in a field is 0, right? So they're always 1. So that's what that was vague, but yeah, that's what I was looking for.
And then on I, it's also what exactly we were
Okay,
there.
so what this has been a while ago, right? If the characteristic of the field is not 2, and the degree of K over F is 2, what can you say about the extension K over F? When I taught this class, I'm sure I made a big deal, and this was implicit in one of your homeworks, although you cannot say it. So what you have is the characteristic of F is not 2, and the degree of K over F equals 2. So it's a quadratic extension of a field that is not of characteristic 2. Then, do you know what's true about the extension K over F?
No.
What's that?
Algebraic.
Well, right, that's true. Certainly that's true. In fact, any finite extension has to be algebraic. But there's something stronger that you can say here. And if you don't say it, some poor French guy's gonna roll over in his grave.
French guys roll over in their graves every time I try to speak French.
It's always any extension of degree 2 over an extension that's not characteristic 2 is Galois. And actually, even if the characteristic is 2, if the field is finite and it's of degree 2, it's Galois. Right. And the reason is when the characteristic is not 2, how many roots do you have in an irreducible quadratic? 2, right? And if the characteristic is not 2, those 2 roots have to be different, right? And once you know that the 2 roots are different, then that shows you that anything in So. Then. So here's what I know. So anything in K minus F must be algebraic, as you pointed out earlier. Since the extensions of degree 2, this must be algebraic. If it's in K and not F, it must be algebraic degree 2. It's got some polynomial here. And it has 2 roots. How do I know that they're different? Well, I suppose they're the same.
Or is it just because it's area?
Well, that's part of it. So. Um, I agree. Everybody agrees. And this implies A is equal to minus 2 omega, which implies omega, which is minus 1/2 A, isn't the field. Here I've used the fact that characteristic is not 2. So since I'm able to divide by that 2, this is an F. And that's going to be a contradiction because this is actually and that contradicts the irreducibility, right? Because now the linear polynomial x minus omega is in F. And there you have it. Or you can this directly contradicts the fact that it's in limit. So it has 2 different roots, omega and omega bar, right? And so you have an automorphism. Here K is equal to F omega. Well, since it's out brackets, F squared bracket. Sigma of A plus B omega is equal to either A plus B omega in case the ideal, or A plus B omega bar in case of because it has to take the root of omega the other thing. And since these are different, you can prove the fixed field of K is actually F. So that's kind of this is something that I didn't emphasize quite as much in your particular class as last time. But if you have any degree 2 extension of a field that is characteristic not 2, it's always Galois. And you can also do the quadratic formula over any field that's not characteristic of 2, right? Because what happens in the quadratic formula, if you have a monic polynomial, you have a 2 in the denominator, right? And that's cool for any field that's not characteristic 2. Right? Right. What other gems of clarity can I drop upon people? By the way, does that make sense, what we did there? How about this one, number J, since we're looking at this. So K over Q is Galois. Or four. How many subfields? Okay, are they contained here?
Is it three subfield contained?
Yeah, because if you're in characteristic 0, which we are here, then, yeah, Q is the smallest contained in any field, or really technically should say a nice copy of Q. How many intermediate fields do we have here? How many? Okay, so where do you get that? What you should think about is you're on the right track. How many subgroups does C4 have? Well, this is a especially easy subgroup for because it's cyclic, right? And a cyclic group has one and only one subgroup of every number that divides the order. So it should be a subgroup for 4, 2, 1. And there you go. That's so here's what you will actually have. So Galois correspondence. This should be all K. And the fixed field all the automorphous all the automorphs Q. And there should be some intermediate quadratic extension. We'll call it E. You want to build one? Don't break out the hammer and nails, build one with Galois group C4. I think I can do it. Like, maybe. So if I add 1 to 4, I get 5. So I'm gonna look at the fifth roots of unity. So 1/5 root of unity is silly, one, but there's actually 2 other complex conjugate pairs, right? Like I can draw this. There's one. And the roots are, well, have any of you ever figured out what the influence of unity are before. Messed around. So in the complex plane, it's convenient to write one is e to the 2 pi I n, right? Everybody okay with that? This makes it kind of easier to find the roots of unity, because if I take the root of this, so here's what I actually get from fifth roots of unity. I get, well, I guess I can start at 0. I have 1 e to the I 2 power 5, e to the I 4 power 5, e to the I 6 power 5, e to the I 8 power 5. The next stop is e to the I 10 power 5, and so I just start repeating it. Everybody okay with that? Sophia, are you cool with taking the exam in long haul?
Yeah,
See if we get that. Yeah. Of course, one, we kind of, that's the one that, but these other 4 should be the roots of this polynomial, right? And notice they're in complex conjugate, right? These two, when you multiply them, you get these two. So the complex conjugate is this. And you can kind of see that too. Because here's e to the I 2 power 5, so whatever, about 72 degrees. Then this one, 4 pi, 6 pi, 8 pi. And they're symmetric about the slime, so they're complex conjugate pairs. But now, just to make my life easier, I'm gonna call this tornado squared, cube, tornado 4, and this is tornado 0. But I don't care quite as much about that, but one's already in the ratios. Now, this is kind of cool because the splitting field of this polynomial, okay, is Q adjoined with tornado, right? Because once I get that tornado, just the powers of it give me all the other roots. So if I, and in fact, it doesn't matter that I could do Q adjoined with tornado squared, it's the same thing, isn't it? Because once I have tornado squared, that gives me tornado 4, and tornado 8, and then tornado. So I can replace this with any of these powers. This is now. Let me show you how the Galois group behaves. Let's just get this, yeah. So let's sigma take tornado squared. So what sigma does is this takes squared, of course, 24, 24 cube square this. They get and tornado cube do tornado to the 6, which is, and that is an automorphism of order 4. Once I tell tornado where to go, then I know where everything else goes, right? So, and notice that or sigma squared takes tornado to the tornado 4. Notice this is actually the homomorphism. It takes everything to its inverse, right? Because it takes this, it takes tornado 4 to tornado, back to tornado, And it inverts these other two. Tornado cube. Tornado two. Once. Twice, three times. And so notice I'm going to get a couple things. This extension is from degree 4, right? Because that polynomial is irreducible. In fact, you can actually use Eisenstein's criterion on the x4 plus. You just replace x by x plus 1, and you will get yes.
Oh, when you got when you set tornado to tornado squared, like, did you know that that was going to be ordered form, or like, does it matter what the?
Yes, sometimes it matters. I got lucky, and I thought about it for a minute first.
Okay.
Because, for example, with other orders of Galois, it might come short of the order, right? But there will be one that generates in
Okay.
this case with these roots of unity. So we've got 1, 2, 3, 4. We've got a cyclic Galois of degree 4. All right. Anybody know what E is?
Complex conjugation?
What's that?
Is it complex conjugation? Or no, is that?
Right. Complex conjugation. So you're right. Complex conjugation should be an automorphism in this field. So, and in fact, this one right here should be complex conjugation. Right? And the reason is, remember, this is tornado 4, tornado cube, tornado squared. What that one does is it swaps these, which is essentially complex conjugation. Right? You're just changing the sign of the imaginary part. What's the fixed field? Yes.
Sorry, will complex conjugation always be sigma squared? No.
No, only
That's
in
just
this
the
case.
order.
Yeah, it's just in this case. Let's see anything invariant in the complex conjugation. Actually, none of the roots are, but maybe a combination of roots are. I'm programming this. So in this intermediate field, the chordic should break down. In the field K, the entire splitting field just breaks down into linears. In the intermediate field, it should break into two irreducible quadratics. I'm assuming this form, I'm taking advantage of symmetry. Let's see if this works out for us. This is x4 plus a plus b x cubed plus ab plus 2 x squared, I reckon. Okay, this is a real good sign. Because notice my cubic term and my linear term are both the same as they are here. So really to get this, all I need to do is solve these equations. And AB plus 2 So this is. And. So let's see, I guess that needs to be as 1 minus A. So this is A times 1 minus A. It's -1. So I get -1 is A squared. So if A squared minus A minus 1 is 0. No. So this means that A is equal to 1 plus or minus the square root of 5, 2. Notice which root do you take? Notice what you can do is you can take A to be this one, B to be this one. Right. By the way, we could have also helped ourselves by noticing that this polynomial is also x minus tornado, x minus tornado bar, or x minus tornado squared, x minus tornado cubed. And the reason I pair them these ways is because these two are complex quantities. So this is x squared minus tornado plus tornado plus 1, and x squared minus tornado squared plus tornado 2 plus 1. So in particular, what we have is the intermediate field that we wanted is Q square root 5. Same thing as Q tornado plus tornado. These two give you the same. I'll give you another new corollary too. By the way, tornado plus 4 is that A or B? A. Yeah, I remember. Positive. Okay, so let's. I didn't put the X's there, but it's still in person. So A is the coefficient of X here, all right? So it's got to be one of these, all right? Now, notice that when you add tornado 4, the imaginary part is gone, all right? You add. What can you say about the real part? Well, the imaginary part is 0. I don't know much, but the real part is bigger than 0. I agree with that. Because I can just look at this thing and see its real part, it's 2 times whatever the real part of that is. And the real part, the other one, is less, right? Notice that this thing is positive, and this one is negative. Agreed. So make sure I get this straight in my mind. This guy, this one right here is positive, but then I've got a negative sign here. So, this thing should be the one that's negative, right? So, well, actually, let me figure this out here. I think it's all by sign. Minus tornado plus tornado 4 should be the one that is positive here, which is, I guess, a right, the root of that assessment situation. So you look at minus two minus, yeah, it shouldn't be minus, it should be minus. Right, because this thing right here, the minus one should be that's positive, so it's negative, so that should go from it's negative. So tornado plus 4 is radical 5 minus 1, which is positive. Everybody okay? This is e to the I 2 times over 5 plus e minus 2 pi. Right, because this is 8 power 5, which is nice, so I can write it that way, right? So this is cosine 2 power 5 plus I sine 2 power 5 plus cosine 2 power 5 minus I sine 2 power 5. Imaginary parts cancel out as hope, and we get so there's a corollary from Galois theory. Ever seen that identity? You might, I think you might need some frequency, but you can do more exotic things. This is actually really, this is also really important if you want to, did any of you ever have a geometry class in high school where you constructed things with a ruler and compass? Right? Did you ever see the Pentagon done?
No.
Yeah. It's really interesting because I saw the Pentagon done when I was in high school, and my teacher, I think, clearly kind of memorized some procedure and went through it. And I was like, wow, this is crazy. Why does this work? Well, it's all this algebra here that really makes it work. Don't let the tractors and straight edges fool you with compass and straight edges fool you. Okay, yes.
So I know, like, obviously there's one, like, 1 is the real root of x to the 5th minus 1.
Yeah.
How do you know that the other part has 4, like, has the 4? I mean, I know they come in pairs, but how do you know that, like, there's not just like 2 components?
Oh, how, why are there not any more real roots, right? Well, I guess the easiest way to know is just to use the complex number right? To write this as so what I'm trying to do is I'm trying to find the 5th roots to this. And the easiest part of this procedure, the easiest way to do this is realize that 1 is equal to 2 pi n for any n, 0, 1, 2. Right, because this thing is cosine 2 pi n plus I sine 2 pi n. And for every integer, that's gone and that's 1, right? And once you do that, then you have x is e to I 2 pi over 5 Yeah. So this repeats on a period of 5, right? So when n is 0, this is just 1. And when e is 1, it's either 2 pi or 5, which is not real. And you can actually check 2 pi over 5, 4 pi over 5, 6 pi over 5. None of these land on the real axis until it gets back to 10 pi over 5, which is back to 1. So what it does is, geometrically, this is kind of not too bad to see. Starts there, 1, 2, 3, 4, and then it repeats. And 1 is the only one that lies on the real axis. In fact, the only roots of unity, by roots of unity, I mean something whose power gives you 1. The only roots of unity in the real numbers are 1 and -1. And -1 does not, -1's not ever an odd root unit, but it can be an even one. Are you guys okay with taking the exam in long 207 next to my office?
Yeah.
I thought it would be more comfortable. Here, I'll let you know.
It was warm.
Yeah.
College exam, but it's pretty,
Yeah, the
pretty warm, yeah.
I thought it might be borderline uncomfortable for y'all.
What did you call it? This message? Right or where?
Oh yeah, that's a word in Sanskrit. It means hot. It's held in either Buddhism or Hinduism. So I culturified myself.
You did one of the questions.
Uh, oh, is this one where you've got A and B? R modules show that the tensor product to free modules is free and so forth. Okay. Okay, right. Here's what else. So F1 and F2 are first. So these are free R modules. And our goal is to show that the tensor product of these two is still free. Now, this is so the first step is just to say, to recognize that that a free module just means some of smaller, right, as addressed. Right? Everybody cool? Next step. Any ideas on okay, I also can tandem this. So here's the fact. Here's the fact that makes the machine move. Y'all remember this? Good. You have A. Oops. And Remember those results for class. Okay, so let's just apply this situation. So what I'm gonna do is I'm just gonna consider this. This is gonna take the place of, in the second line. B. Right, so this should be direct sum. I and I. R. Tensor. B. And my B is direct sum. J. Right, just letting that kind of be and what's. Now, on the inside of this, I'm now going to apply the top one. Right? And this will be direct sum of direct sum like that. Like groovy so far. So what's another name for this stuff? It's kind of crucial here. There's another fact. And that is you know what this is isomorphic to? Y'all remember this?
One. It should be just one tensor A.
Well, say.
Yeah.
That's right. You think tensor should have so this thing right here. Star. So this is isomorphic to some big direct sum. So it's just what you call small over bigger, perhaps index set. Right, okay with that? Now, this is building to something, just like Randall Graves' career. So, part B, I must say, yeah, that's. Okay. You able to solve B? You able to do B? I'm. Well, it's a very good thing if you can't do it. It's just flat wrong. I must have corrected this on the test. That didn't work. Well, so here's the claim. Let's take apart the claim.
I knew you were giving institution.
Show if a tensor B. Okay. Then, I can get all right. I hope I correct this. Oh, Susan, very sad. Yeah, this is easy. So here's some stuff we saw in class. Let's just make our life easy and look at see. Uh, uh, I'm sure there's a better example. One place. let R be the same, let A equal Q. And we know from class Q was, not projected. I proved that. It's actually a flat module, if that's your code, it's not projected. The zero module is projected. All right, and so the product of this is zero, which is projected, the Q is not. So, yeah, here's something that I know to be true. And I, this must be this typo. Is supposed to be on here. No, it's if A and B are projected, then the tensor. I'm smart enough to thought this because when I start showing you why this is true, you'll see it builds off the previous. Okay, so first of all, let's just assume for the moment that A and B are both projected. Shantanu, are you okay with taking the exam?
Oh, I'll take the example there.
Yeah.
I thought the review was over, but yeah, I'm good with that.
Have there been any stray sightings?
I mean, mechanics.
Okay, so maybe you'll answer my email. So, if A and B are projected, then A tensor. What does it mean for A to be projected? Now, there's the definition, but there's an equivalent way to think of it. Maybe in my time with the previous one.
It's free sum trivial.
What's it?
It's free sum trivial.
No, I think you got it kind of backwards. It is the direct summand of a free module.
Okay.
So there exists R modules. M, such that some right? That's what it means for a module to be projected equivalently. It means it's the direct sum free. So I can find some other modules, which by the way have to be projected, that I can glue to A and B and make it free. Now, let's look at this. And okay, this is kind of an exercise in knowing how to do the tensor product here. So let me take this step by step so I don't confuse my piece of the brain. This is A sum. Let's see. Tensor B. Direct sum. A. Agreed. So it distributes like you would expect it. Right. Like you would expect multiplication distribute over addition. And now let's do more of this damage here. A. Right, sum A. I'm sorry, M. Break some. A,
You don't need to do that side to me.
what?
Do you need to expand it fully?
Yeah, you don't need to, but I'm going to. I see your point, you're right, but. You know. I agree with it. That's the way that you fully spend that out. It's sort of like foiling, if you will. Right? And so what? What do we know about this one? This one. Why? Because we just did that in part A. What do we do here? We tensor to free modules. It's got to be free in part A. And so A tensor B is a sum. So does that make sense?
Question, or what exam is it?
This was spring 2013 final exam, and let me cost you, I don't know all that happened, but 2B is incorrect. I'm not, you can find the file, and fix that.
In each of those sums.
That's exactly right. Each little piece is, each one of the sums is also. Okay, other questions? Tell me about free job. Yes.
Can we do another example of computing Galois group of a polynomial build?
Do you have one in mind? Because if God picks one for us, the Galois group will be SN, right? So,
I mean, you could just do the one on the top right.
oh, okay, yeah.
Do you do the last one, which isn't transitive? It's not.
Let me see. Yeah, I'll do whatever you want. Let's see. Is that homework? 11?
Yeah.
Yeah. So the first question, the last one, what the x6 minus 4?
Yeah.
Okay, so this is Galois group over Caesar. Well. See this polynomial is not here because this is. So the splitting field is what we get when we join all the roots. Right. Well, the roots 1/3, omega 2 to 1/3, and it's complex constant. laid out. This. Yes,
This is back on that one. I don't think about like A tend to it's symmetric, but how do you know that like M tends to? Oh wait. How do you know that F tends to B plus like A tends to B? Like, how do you know that that's true?
I don't, I know the whole thing is
Oh,
the
okay.
whole thing, because where this came from, this is free and this is free. And in part A, we proved whenever we tensor two free, the whole shebang's.
Okay.
Okay, notice the roots of this are right. Because cube root -1 is -1. There are other cube roots, but they intermingle well with these. So the upshot of this is if I take Q and join all the roots of this polynomial, I only need these three roots out of this. Right. Do I agree with that? Because the roots of this one are just the minus signs of the roots here, so there's nothing to name it, right? So in this case, K and the Galois group of K Q is S3. That was actually the first example that we did when we started talking about Galois theory, right? Because there's a couple of ways to see this, because really what you're looking at, instead of looking at the splitting field x to 6 minus 4, you can compact that and say, well, it's really just the splitting field x cubed minus 2, right? Because you don't get anything new from the other factor. Sometimes you might, but this time you don't, right? And so we can look at the polynomial x cubed minus 2. That is an increase in cubing. So it's only got one real root. So it's got exactly two complex conjugate roots. And we also have a theorem from class that says the Galois group is SP. But so notice that the Galois group should act transitively on the roots of this irreducible piece. So there's automorphism, this to this, and any pair of them, there's an automorphism, there's one together, and you've also got complex conjugation. So S3. Okay, so far. Hello? Okay, we also note about substitution. The words this look like. So again, using symmetry. Let u equal x cubed. I can actually get the roots here. 3 plus or minus the square root of 5. See. So I can list what the roots are. I've got 2 new ones. 3 plus 5. 3 minus 5. And those two better be input with each other, because the other 4 roots are non-real complex roots. And so I did notice that every given an element that's a root, then its inverse to the root. So since this is it must be inverses of each other, and they are. If you multiply this, you get 9 minus 5 and 4. And your other roots are, I'll call this alpha. I'll call this alpha inverse. Alpha omega, alpha omega bar, alpha inverse omega, alpha inverse omega bar. Where omega is so we counted for all 6 roots. And notice they are in inverse pairs. These 2 are inverse pairs. These 2 are inverse pairs, and these 2 are inverse. Now, another observation. What's the degree of the extension? Well, when I did the substitution plus squared, I get this extension here. Now this extension is 3/2. Right? Now, how far up do I have to go? Notice this contains because any field that contains alpha has to contain its inverse, right? So that's going to contain field roots. Now, where do I have to go here?
You have to join the cube root unity.
Okay.
Or cube root.
Well, I could do this. Because alpha wasn't with I can still hit it. Notice this contains alpha to the 1. Actually, I shouldn't have written this. The real roots are I'm almost confusing myself here. So I have roots Here are the real roots. These are still inverses because basically we multiply these two things in the cube root, under the cube root together to get one. So again, the roots are alpha, omega, alpha inverse, omega bar, alpha inverse omega, alpha. Right, and now these two are inverse pairs. And there you go. And this is 3, 2. This is 3, 3. You might ask yourself how you know that the cube root of this isn't already in this field extension, but it's not. It's degree 3. And then you, as you pointed out, you have to get the cube roots of unity. And once you have alpha and omega, that's the splitting field. You get all the roots. So this is looking like in this 312. Yes.
Is omega, like adjoining omega is a degree 2 extension?
Mhm.
If we
It's
take
a root of x squared plus y.
plus,
It's a root of quadratic.
okay. Oh, so,
It's a very cube root one, so it's a root of quadratic.
okay. It's the root of quadratic.
X squared plus x plus 1.
Is it, are all the primitive roots of the form of, like the nth primitive root, as in like one of, like if you have e to the I 2 pi over n, that's the primitive nth root? Okay.
That's right. Right, so this one, okay. So, um, we have these roots. We also know complex conjugation. Some of the roots are complex, not so complex conjugation is not one. We also know that Galois groups are transitive. So, given any pair, pick any 2 out of 6, there's an optimal together. So, I never get this right. Let me make sure this works and it's on this through it. This goes to alpha inverse. Beta, or yes. Or
The third step should be alpha omega bar inverse.
Omega. Or. And that goes to alpha, omega bar. Okay. So, I'm gonna show you how Galois works. There is an automorphism that takes alpha to alpha inverse something. Everybody agree with that? Now, in this field, if I tell you where to take alpha, and I also tell you where to take omega, that completely determines the arguments. Right? Because everything in there is either in base field or it's product style. So once I tell you where those two go, we're solid. Ready? There is an automorphism that does this. Also solid, all right, because that's just another root, right? Now, one of two things happens. This automorphism that I picked, call it sigma, also conjugates this. If it does, then let's just pretend for right now that the sigma takes alpha here and also conjugates omega. Right? Let's follow the order. Alpha goes to alpha inverse omega. By the way, that means the inverse of this goes to the inverse of that, which is alpha omega bar. So when you compose it, now alpha inverse goes to alpha omega bar, and that goes to omega bar, so that comes to alpha omega. This now goes to alpha inverse omega times omega bar, so it just goes to alpha inverse. Notice this composition is just taking it to its inverse. Do it again, alpha omega. Do it again, that's alpha inverse omega times omega, which is alpha inverse omega bar. Finally, do it again, that's alpha omega bar times omega, which is alpha. So sigma has order 6. Right? Now you might say, but Jim, what if sigma doesn't? What if sigma that you pick leaves omega alone? Would you mind? Then I'll say, I don't care, compose it with complex conjugation, because we know the complex conjugation is known. So just take sigma and compose it with complex conjugation, and that'll do well. Everybody okay? So there exists sigma in the Galois group such that the order of sigma is equal to 6. Right? B, complex conjugation. So the order of phi is equal to 2. Right? Now again, all I got to do is know to determine the automorphism. All I got to do is figure out what it does to both alpha and omega. So let's look at what does this do? Well, this conjugates it. Right? That conjugates omega. And this, well, we did say that sigma also conjugated omega. Do I agree? Which is the same thing as sigma inverse. Because this is sigma inverse, right? It just runs it back, takes alpha to alpha inverse omega bar, and it also takes omega to omega bar. Everybody okay with that? Now, look at complex conjugation sigma on alpha. Well, of course, alpha is real, so complex conjugation doesn't do anything. And then this is complex conjugate of alpha inverse beta, which is alpha inverse omega bar, which is so if you look, you have sigma to the 6, it's complex computation, which is the identity, and this generates a copy of these 6. This is valuable functions. It's
I remember that we did like, if you permit the roots, it's a well-defined automatism, but to be able to prove that the Galois group is transitive.
Sort of, and I'll show you where that comes from.
Yeah, I remember we did the example and then we constructed like the basis full of the roots, but is that full in a general sense?
Right, because what happens is, let alpha, beta, the roots, irreducible polynomial events, and, well, I'll just talk about qubits, versus. But alpha, beta, be roots of the series polynomial, let's assume they're different, but actually they don't have to be for one of six. Then, right, and this is, when we discuss this is isomorphic X, while the idea of X. And so is this. So, because these fields, they can't tell the roots apart. And so this induces an isomorphism between alpha and beta. Now, this, you can lift this to an automorphism inside the splitting field where you've got all the roots, right? So, given any pair of roots right here. That's why the Galois group acts transitive. For any pair of distinct roots, I can induce an automorphism.
How do you? No.
In principle, couldn't there be, like, this isn't, when you're saying, like, in principle, you did show that, sigma and, phi are the only, like, that there is something that is, generated by that.
Well, they certainly generate a copy of that IHEDA group, right?
Yeah.
That means that whatever the Galois group is, that's a subgroup isomorphic IHEDA group. So that means the degree of the extension has to be at least 12.
Right.
It's no more than 12.
Right.
So there you go. So it has to generate all the Galois group. Yes.
I have a follow-up question. If we take the isomorphism and then we're trying to lift it to the splitting field, what do we do about the elements that weren't in our original isomorphism?
So, all right, let me see if I can wrap my head around the question. So, all the stuff is sort of contained, no, we didn't put the fundamental there. Galois theory. Let me see an example to illustrate. Well, I think this is good. So let me try this. So this gives. This gives a homomorphism, so this is like, these are two different roots, this polynomials, again, so we get an isomorphism from this field to this field, but they're different fields, right? They intersect in the. Now, if you read the splitting field. Well, that's a heavy-handed way of doing it, because what I've done is I've put on three roots and put it on this. Now, what you can do is you can do this in pieces, I guess, because in this first field, so let's just start with me. This thing loses its irreducible status, right? So this now factors as x minus 2/3 x squared minus 2/3 x plus 2 to 2. Oh. This is what it is. So what happens is we go to third, this polynomial snaps off. And now what you have is you have if you want to continue to, in order to splitting field, you have to join the roots of this, right? This is basically the other two roots of the same thing. So, now there is this original map that we have here. You can actually visualize this as part of this Galois. So, and in fact, a basis, right, take basis 1 to 1/3, 2/3, alpha, alpha, 1/3, alpha, 2. And see, this is more than just basis, right? Because these elements interact with each other algebraically, right? I mean, it's this set right here is linearly independent of the cube, right? But there are also multiplicative things. In general, in vector space, you can't multiply them to the basis, but here you can. You can take this thing and cube it, and all of a sudden it's no longer independent, right? So you can think of this homomorphism that we have right here, this isomorphism fields as being just part of determining this vector space basis, right? So what I can do is I can take this to omega 2 to 1/3. That's another basis on it, right? And well, once I do that, I only need to specify one more thing, and it's going to determine this multiple relation, right? I mean, normally, if you've got a 6-dimensional vector space, right, you have to tell every basis element, right? And that determines this. Well, this is a vector space too, but there's extra stuff on it. Like, for example, 1 goes to 1, and this, in Bermudian spaces, right? Because we're assuming that this is also field homomorphism, so that's freeze values. And because there's a multiplicative relation between the bases, they're linear in. This also calls this. Whatever happens, this has to go to omega bar 2 2/3. Now it's still not enough information because I just gleaned this from where I sent you for a third. I also have to tell where to go down. Where I didn't know. I need to tell it where omega can go. And there's only 2 places omega can go, and that's to its conjugate or to itself. Right? And whichever choice I make is going to tell me where everything else goes. Because I've already got this piece. Because again, this is not just a vector space homomorphism, it's a field homomorphism. And the polynomials, the algebraic relations are controlling what's going on. So omega is either going to go to itself, in which case this will go to omega bar 2 1/3, and this will go, I guess, to omega 2 2/3, or omega will conjugate. And in that case, this will go to I guess 2 1/3, somewhere else, right? So anyway, so after all this rigmarole, I guess the short answer to the question is the other things that aren't there are also controlled by the splitting field by the relations. Because the splitting field here has 3 6s a vector space, right? But when I'm generating it this way, and I did this to help me build a good basis, when I generate it that way, I've only got 2 sort of things going. And actually, I didn't ever get this theorem in this class, but there's a pretty development theorem. Here I can actually generate this sort of 2 by 1. Guess what I can use? So here, the splitting field, you throw in all 3 roots. But I said, oh, look, I can do it short. Anybody think of the way I can do it with just one element?
Omega multiplied by 2.
Omega what?
Multiplied by 2.
No, because that's just another root. That'll only give you 3. But I bet if you add, so if you take 2 to the 1/3 plus that, and that will make kind of a messy basis too. That's why I picked doing separate ones, because this thing has an easy polynomial, so degree 3, and this thing has an easy polynomial to degree 2, and it helped me to keep things from getting out of hand more quicker. I suspect when you put a question mark on this, there's the primitive element theorem, so I guarantee it's some element, and I would bet precious parts of my anatomy this would work. And the reason is there's just no way. So this certainly generates a subfield, right? So this has to generate a subfield of this. So the extension of this over Q has to be a degree 2, 3, or 6. And I don't see any way that thing is going to be. Well, this thing is certainly not in This is certainly not in the rationals, so it's not a degree one, because this is not a real, right? I don't see any way that this is going to be degree quadratic or a cubic. So if that's the case, if it's not, then that thing would work. So I could make a basis out of that by just looking at powers of that. But you see where the powers are, they're going to be awful. We will have terrible polynomials, which is why I use the two elements that have some representation. But yes, you got two roots like this, then when you go to the splitting field, you can preserve this, and this lives to an automorphism. In fact, that was one of the things in the fundamental theorem of Galois. Yes.
This one, the degree was 6, and it was like D6. So if the n corresponds to the degree of n, right?
Which you know what I'm talking about.
The like dn.
Oh, so when I use the dihedral group of Dn, that is the dihedral group on the n gon. So D4 means dihedral square.
So would that like the polynomial is degree 4? If it's irreducible.
No, it doesn't have to be. So let me also make it before I go on. Dn has two n elements, right? You can't just look at the Galois group, unfortunately, and say, okay, now I know what. Here's what you can say. You can look at the Galois group and say, I know that's the degree of the extension of this Galois. So here we got Galois group D6, right? Okay, here's what I know. That extension is a degree 12 because that's the same as D6. What I can't say is, okay, that came from a 6th degree polynomial. So, I mean, there are certain things you can bound it a little bit, but you can have yeah, you can certainly have a 6th degree polynomial as an example. Well, it couldn't have the Galois group as 4 if it's irreducible, because the Galois group has to have an element of order in it, right? That was one of the things, but like for example, I don't know here. Because I think, for example, yeah. I'm not going to get bigger. So the question is, now correct me if I'm wrong, but in fact, I think that there are. I'll get back to you on that. I'll give you an example, but I'm sure that, so for example, you can have an isomorphic Galois group for one. So what could happen is you might have a Galois group for a small polynomial and then a larger polynomial, perhaps. So in other words, knowing the Galois group, what you can tell is you can tell the degree of the extension, but I don't think you can do that to say, okay, this came from the degree polynomial. Something like that.
Does the degree of the polynomial always divide the order of the Galois group?
It's irreducible.
If it's irreducible.
All right, so if you've got an irreducible polynomial, say it's irreducible degree n.
Okay.
So you look at the Galois group of that polynomial, so that's just the degree of the splitting, or that's just the, if you look at the Galois group of splitting field. That splitting field will be a transitive subgroup of SN, and it has to contain an element.
And if it's not irreducible,
Oh, well, if it's not irreducible, then, I mean, then what can happen is just break it down into irreducible pieces. Sure. Right, and so you could have something like, well, a good example would be something like, you look at this polynomial. It's that. So that one, so really, if what you're looking at is the Galois group, that polynomial, you're looking at the Galois group splitting field. Wow. Sure. Right, and so what you're looking for is, now you take Q and adjoin with the square root of -2. And now you take that and join the square root of -3. So that's going to give you a fourth degree extension, and Galois group is going to be C2, C2. Sure. Right, and so you're, let's see. Yeah, so, yeah, well, let me correct something that I think I spoke earlier. So the Galois group, if you have an irreducible polynomial, it's a transitive subgroup of SN. And the order of the Galois group is by n. It doesn't necessarily have to have number. But the order of the group has to be divisible by n. So here, this polynomial is not irreducible. And the Galois group here, I think, is C2, C2. Right, because basically the isomorphisms of splitting field of this, you're just going to swap out square root of -2 and minus square root of -2, the same square root of -3. So it's going to be the C2, C2 structure. Yes.
I have a question about this still. I understand that the first part comes just from like the multiplicative structure of homomorphisms. But can you explain why we still have this constraint on omega? Or like where we can send omega to?
Oh, right, because omega is the root of right.
So we just
So
choose.
because omega is, I mean a specific omega here. That's the primitive cube root of unity. Omega is a root of this, right? So the automorphism, this automorphism has to fix Q, right? And so that was one of the things that we had here. So this is an irreducible polynomial, Galois. And so omega is a root of it. So any automorphism that fixes Q has to take omega to another root of the same irreducible polynomial. And in this case, the only thing you've got is complex times.
So we can send omega to either itself or the complex conjugate, but we just like kind of choose and see what we get.
Yes.
Right.
Yeah, in this case, you can. That's right.
Wait, alpha's not in the in Q. Why consent? Is it alpha?
What's alpha?
Two to the Q or 2 to the 1.
Oh, why can we not send it to its negative?
Or why can't we send omega to that if they're both not?
Oh, because the roots are different polynomials, right?
Okay.
So the minimal polynomial, is x to the minimal polynomial, omega is x squared plus x to the 1. So there, yeah. So they're not roots of each other's normal polynomials, so you're never gonna go there.
Dr. Colville, in general, when you have an x at the end minus, 1, is it always, reducible?
Oh, that's always gonna factor x minus one in it.
Right.
And if n is even, it's got another factor.
And then, you have x to the n minus a squared, then that's always reducible. Or x to the n minus a to the n.
Yes.
I'm looking at your 14.5.8, and this is like when we were doing the stuff with like the resolving cubic stuff. That like, how can the degree of
Oh, by the way, with all this stuff that I was showing you, that's kind of fun. Don't try to memorize that stuff.
Oh, okay.
So, please,
So we don't need to know like if m equals 6,
don't
then it's
memorize that stuff.
okay.
Yeah, I don't expect you.
I do have a question on like, because m is the degree of like the splitting field mod.
N is the degree of K adjoined with alpha beta gamma with Q of this.
Okay, yeah, what that field. How can like if because this is from f of x is degree 4, right? In this case, like so how can like the degree of the splitting field be higher? I thought the degree of the splitting field was wait, is the degree of the splitting field less than or
It can be up to 24.
Oh, okay, so the
Right,
degree
because remember, if you have an irreducible degree n, it's contained in the split field of degree less than or equal to n factorial. So here's how this can happen. Here's your worst case scenario. You come along, you've got a 5th degree irreducible polynomial. You want to break it down, you want to find the splitting field. Well, take a root and adjoin it. Bang. That's a degree 5. Now, here's your worst case scenario. Up in this new field, you've got x minus that root just uncovered. And then you've got a quartic. That quartic might be irreducible in this field. And it's like, oh crap, now you've got to do it again. So now you throw in a root of quartic. So that's a 4th degree extension over what's so you're already up to 20, right?
Okay, so
and then it might break down into just a linear and a cubic. And if you have to go the whole way, and you often do, unfortunately.
Okay, so the first root you adjoin is like the
It's an extension of degree n if that polynomial is
is
irreducible.
irreducible, and then okay.
So let me contrast this. If you adjoin a root of this, it wouldn't be a 4th degree extension because this polynomial is not irreducible. Breaks down into here. So when you adjoin one of the roots, it'll actually be a quadratic extension.
Okay.
Right, but that's just polynomial reduced on. Yes.
I had a question about the, when you had the, x is 6 minus 2. I think it's that one, where you had, no, x is 6 minus 4. So you have x cubed minus 2 times x cubed plus 2. Over there, you make sure that you're, when you permute your roots, they have to stay with the same polynomial.
That's right.
But that doesn't apply to this x to the 6 minus 4.
Yes, it does.
It does.
Yes. There are 3 roots of both of those polynomials of the factors, and they all stay within that same polynomial.
Okay.
It's just the second polynomial, all the roots in the first polynomial, roots of the second one vary by sign.
Sure.
Right. So it's sort of like what you have there is this. all these roots just move in here. And this is. None of these is root of that, and none of these are root of this.
So you can't send two to the cube root.
You can't send two, you can't send, you can't send, the cube root of two, real cube root of two to minus root of two. Because if you could do that, that would cube that, that would mean that you have to send two negative.
And you could do that if it was even.
Yeah, that's right. Right.
So if I had x squared minus 2 times x squared plus 2.
Yeah, so you had that. But he's still what you have, you have plus or minus radical two, then you got plus or minus I radical two. And again, they're gonna be segregated, sure, right? Because neither one of these is root this, and vice versa.
So whenever you have reducible, they just stay their own little things.
Well, let me rephrase. Whenever you get down to the irreducible factors, the roots of those irreducible polynomials stay within there. All right,
And that's over that.
that's over where you feel that they're irreducible.
Okay.
Right, that's right, because I mean, when you go up to,
The point is to make the.
right, I mean, if you would join square root of two to the cube, all of a sudden this breaks down into two linears. And there is an automorphism fixing Q that will flip those. However, if you now want to fix Q and join with the square root of two, now you wouldn't allow that. Right.
So it's that x squared minus 2 times x squared plus 2, is that also z2 z2?
Looks like it. Right, you can send plus or minus radical two to itself. You can send, or you can send radical two plus or minus radical two. You can send I radical two plus or minus I radical two. And whatever you do with those two, it tells you what to do with I. Correct. Right.
So they don't stay segregated?
No, that's not what I'm saying. But what I'm saying is, so this is again, because of the fact that this field and you draw multiply related. So let's suppose you take radical two minus radical two and I radical two, I radical two. So you flip this one out and leave this one alone. Then I radical two goes to I radical two minus radical two, which is minus I. So if you do this, it also conjugates the I. Yes.
How much do we need to know about like integral closure for
Know what it is, right? Know the definitions. Yeah. Know what evaluation domain is, what this is. So. Yes.
Chapter 5.4, we can just like.
What's not?
That was the like approaches to finding Galois. Other than like other than like the proposition, where it's like the order and like the separate part,
Oh, yeah.
like the actual like.
I'm not gonna, I mean, if I wanted to do it for a bottom, which is kind of close, but if I did, I would probably give you something to work with.
Okay.
I don't want to just give you some 6-degree polygon and say, knock yourself out, kid, because, you know, if you haven't memorized that stupid crap, then I get nothing. There's big tears, it's sad.
Yes.
Yeah. And if you get it right, I'm even madder, because now I've got to read 3 pages of work, and so.
So we're not gonna have to calculate scale well? Or we will?
You're not gonna have to memorize all that stuff. I did that kind of to show you how to do it or whatever. I don't expect you to do that on the test. I mean, I hope you can tell me what the Galois group is, Q, which one of the square root of 2 of the cube is, or something like that. Galois group of C over the reals, something, right? But I'm not gonna like make you go through, figure out how to resolve it, probably not. Right? I'm not gonna do what I do on homework because you don't have that much time.
Oh.
Did we do proof for the fundamental theory that while during class?
It was spread out over a few lectures, right?
Oh, okay. Yeah.
There were lots of pieces to it. Yes.
Are you gonna have office hours tomorrow by chance or no?
Well, I wouldn't count on it too much because I'm giving an exam from 10:45, and then from 11:30 to 2, and then I've got a meeting at 2:30 to 3. So, and then I'm going home with I have to cook a whole bunch of hamburger. Probably, so. But I'll be in, I'll be in by 7. The exam that the morning exam. I'll probably have to be out there by. What time is the exam here in Stone? Is it 11:30 or is it? Well. It's 11:30, isn't it?
No, I believe that.
Because it's 8:30.
10:30.
No, it's
No,
11.
yeah, 11,
What,
it's
wait,
every
what,
30
what
minutes.
time's left the class?
What's that?
What time's left is the class?
Oh, no,
I mean, I guess there'd be an overlap.
yeah, so the time slot would be 8 AM. when it was Friday. But I think that it's 11:30 to 2. Yeah, it's 11:30 to 2. Yeah, because they give you an hour, I think, from one end to next beginning, so. Anyway, the point is, I'll be in my office from like probably 7 to 11 tomorrow, because the exams I'm given are like, people with extra time, so.
Oh,
It's
you
wise.
in your office from such and so?
Yeah.
Yeah.
Growing up, I was at yes, plan. Right? Finds a way.
There any topic?
Yes.
Let's see, where do we start? We started with modules, right? You got a big gal out there, yeah. What's that?
Is, you'll have questions on the canonical forms?
Yeah.
Are there any like, I know you were saying like some of the questions on the last semester final were like sort of things they like to see, like the department likes to see. Are there any topics like that?
Not connected. You got too rarefied. Yeah, you're right. So on the, yeah, so like on your 4120, I have to put 2 8 point.
Yes, so there's not gonna be any 8 point.
No, they're all fives and threes.
I specifically 2 8 point questions.
What's that?
Why specifically 2 8 point questions?
Because the department does this. Looking at how the majors do in these 4 classes. So whatever you starting with 9 or 41, say, would you please put a problem or two on there that you think is central, problem, and then tell us how this. And then I'm sure it goes into some file, but then whatever says again. So that's what I do. I make it out of 8 because I think they like percentages to be quartiles, right? And so it's easier to do it that way. And usually the 8 point problems are, in my opinion, easier than the ones I would pick myself to ask. They don't give me, I just specifically concentrate on this kind of big picture things. So they're questions I ask probably there. Or I would. Yes.
Where would we find more problems to look at? Like, you know of any resources beyond like your previous exams?
You would buy like 20 old homeworks.
Okay, then that would be the one thing that would be
What
relevant.
kind of problems do you want?
I guess mostly on Galois theory. Just look at the textbook.
Yeah, there are specific texts on Galois theory. And I mean, if you really want to knock yourself out, just use a computer algebra system that'll compute with Galois groups on it. Maple through it, some others. Make up a polynomial and check if it's irreducible, and if it's irreducible, so you can tell what Galois group is. But if you really make it up, I'll tell you what the answer is. What degree do you want to make it? 5. Irreducible. The Galois group is S5. In a certain sense, most polynomials. Right, that's why polynomials on your homework and things like x6 plus 3x cubed, things like this, they're very symmetric. Because if I just made it up at random, I mean, you can bet your bottom dollar I did the problem first, because I just make it up at random.
But if I do the Galois group over R, then it's at those 2, right?
Yeah, it's over R. Yeah. But I mean, if you're over Q, so. Can you explain why? This would be a good problem. Guess I can ask. Explain why the Galois group got polynomial. No matter what A, B, and C is a solvent group. Solvent group. I mean, I didn't even tell you if it's irreducible, right? It could be, right? Take A and B to be 0 and C to be like, I don't know, -64. And this is reducible. But I promise you, Galois group is solvent group. Because in your worst case scenario, if it is irreducible, it could be a transitive subgroup of S6, And there's 16 of these up to isomorphism, and some of them are very not solvable, right? S6, A6.
Used to like a substitution. He's rough. Yeah, because if that's all one, it's just like this. So that is.
Any cubic is solvable. Because that thing's got a lot of room. It's a transitive subgroup of S3. These are always solvable proofs. And so, means I can solve that. Then I can solve the original polynomial just by extracting the square root, which means whatever the Galois group is, that polynomial is solvable. And so notice the symmetry there. If I change that, if I change the exponent x4 to x5, yeah. I'll beat the spirit out of it. I'm not gonna ask anything that's that involved. It's too much. I mean, with no definition. Actually, something about the guy like this, so he can get that. You know, always puts those problems. There's always a homework in here. I have to do the Galois, do the Galois groups, it's all numbers because it's fun. It's really my attention. Oh, it's fun, it's 3-7. But inevitably what happens is everybody's like, oh my God, he's gonna put this in the exam, this. It's like, yeah. Think about how long it took you.
Assume there's not gonna be any like gigantic diagram chasing.
You know what I should do? Here's what I should do.
A dagger.
I should like give you a polynomial and let you all get out your phones and ask ChatGPT.
Oh.
And first of all, let's see if everybody in the class gets the same answer. Which it might be good enough now where it is, although I might be able to trick it if I think about it. And then let me give you a cracking at it and say either confirm or refute this answer.
But in that same time, you could just go, you just write the magnet.
Yeah.
How many points is the final to be out of?
Yes. It's up to 80 something now. My guess is it's low mid-90s. 4120's 100. So, well, I mean, think about it. I mean, given the number of, I mean, probably not going to be 50% more as far as points go. More of those points are going to come from writing the definitions in.
Did you put think evil on 4120 up there?
What's that?
Did you put think evil on 4120?
Well, we'll see. You know anybody in 41 place?
I do, I won't call. like this thing. They started watching the.
I sort of.
Well, that's true.
I don't guess. Any more questions?
Yeah, don't answer.
That up my answer.
Yeah, maybe it did switch, maybe they started. They watched the entire 40 minute